Let's remember matrix multiplication first. So if we have a matrix, say S, this is a 2 by 2 matrix, and we have a row vector V, we can multiply V times S. And to do this multiplication, we're going to look at the row vector and do the dot product with this first column. That will be the first row, first column in the answer, and the dot product in that case is 12. And then we do the dot product of the vector with the second column to get the second entry of 18. So multiplication is always a row and then the dot product with each corresponding column. If we have a matrix rather than a vector, we just work our way through each row in the matrix that's on the left-hand side to create the corresponding output. If we had the same matrix S and the same vector V, if we try this on the other side, S times V, then when we try to do the dot product of the row with the column, then the dimensions don't match, and in this case, the product is not defined. So, reminder, the number of columns in the matrix to the left has to match the number of rows in whatever is being multiplied on the right. But if we transpose the vector, then the row vector becomes a column vector, and in that case we can do the calculation with the matrix S times the transpose of the vector, and in that case an answer is obtained. So one way that we use matrices is to contain information. In this case, information about a square. We have a square that has its corners on particular points, and we can think of those in terms of vectors whose tail is at the origin, and then we have a matrix where each corner of the square corresponds or is given by one of the rows in the matrix. So if we have a matrix, say A, it's 2, 0, 0, 1, and we multiply M by A, then we end up with another 4 by 2 matrix that corresponds to a transformation of each of those vertex points, the corners of the square. And in this case, what happens to the square is the bottom left-hand corner is still at the origin, but now the square has been stretched out. In the x direction, all of the x values have been doubled. The y values have been left alone. If instead we had changed a value in the second column, in this case, we have the matrix B and we multiply M by B, we see that that affects the y coordinate rather than the x. And so the scaling happens to stretch the square upwards in the y direction. If we combine both pieces with C, we have the 2 that we had in matrix A and the 3 that we had in matrix B. In this case, we see that it scales in the x direction and scales in the y direction. So the one matrix takes care of both aspects of the scaling. We do a transformation in a different way. In this case, we add another value in the off diagonal. We change where we had a 0 originally, we put a 1 in there. Now what happens when we multiply by m? We notice, again, going through each entry, every time we do the dot product with the origin, everything is all zeros. So this type of transformation, the scaling or the shear, leaves the origin fixed. The other values, in this case, we notice that there are some changes in the output. 3, 0 is still the same as before, but the 0.33 becomes the 0.63, the 0.03 becomes the 0.33, and so we see that, again, the origin stays fixed, the 0.30 stays fixed, but then the other 2 points are changed as a result, transformed as a result of this shear. So the scale is off in this picture, but the square has been tilted to the right, transformed into this other parallelogram. So we have scaling, now we have shear, and now let's say we want to undo the scaling. If we want to undo the scaling, we start with our matrix A that involved doubling the x value, and to undo that, divide by 2 rather than multiplying by 2. And what we have in this case is what we call the inverse of a matrix. So A inverse will undo what A did. And to check that, if we multiply A by A inverse, then notice that the end result is the identity matrix. And so if we apply the identity matrix to a vector or to a matrix, it leaves those entries unchanged. And so, in other words, it reverts back to where it was originally. So if we applied matrix A to our square, and then applied matrix A inverse to the resulting shape, it would take us back to the original square. In this case, the thing about the inverse matrix here is if we reverse the order of this, then we also get the identity. So if we did the multiply by 1/2, which is scaling by shrinking, and then multiplied that by the matrix that corresponds to doubling, again, that would bring us back to the original place as well, so the original square. Again, remember that most of the time, the order that we multiply matrices really does matter. That matrix multiplication is not commutative. But in the case of the inverse here, the order doesn't matter. We can multiply a matrix corresponding to a shape by one matrix and then the other, or in reverse order, and the end result is it brings us back to the original. If we want to undo the more complex scaling that we had, where we did both scaling aspects at once, it turns out that we can do that in the same way, do it both at once, replace these values with 1/2 and 1/3. If we check that, do the multiplications, the dot products, and the end result is the identity matrix as we hoped. So doubling in the x direction and tripling in the y direction, we undo that by taking 1/2 in the x direction and 1/3 in the y direction. If we have the shear, it transformed the square into the parallelogram. If you added, we can undo that with subtraction. And again, if we do this check, we see that the end result, after going through each row and column of the matrices, that the end result is the identity, and this matrix undoes the shear that's created. So we have the square gets sheared into the parallelogram, and then applying D inverse brings it back. If we had done this in reverse order, we would have started with the square, sheared it to the left, and then the matrix D would have brought it back to the upright square that we started with. So now what happens if we have multiple transformations? If we have this matrix S and the entries are 1, 2, 3, 4, there's multiple things going on in here. There's some scaling, there's some shearing. We scaled the Y value, and we've sheared in both directions in the other case. So what would the inverse look like? Well, we could try the same kind of thing that we just did and said, okay, well, we have this shearing, so let's undo that. We have shearing in this direction, let's try to undo that. We've multiplied and scaled, so let's try to undo that. And unfortunately, it's not quite like that. We end up with something completely different that's not the identity. Just multiplying all of these pieces does not do what we want to do. Now we could go through very carefully, undo one thing at a time, see what effect that has, then undo something different, and we could build an inverse matrix. It just doesn't build exactly in this way. So what do we do instead? Well, let's think about our matrix 1, 2, 3, 4. What we're looking for is another matrix that we can multiply by this to get the identity. So we can go through and look at each of the particular values. And in this case, we notice that the dot product of these two values needs to give the value of 1 because that is the first row, first column. So A plus 2C has to equal 1. And then we continue through the rest. We see that A plus 2C has to be 1. Second row, first column, tells us that 3A plus 4C has to be 0. When we go to the rightmost columns, then we have two more equations. B plus 2D has to be 0, and 3B plus 4D has to be 1. So we have really 4 equations in 4 unknowns, but they separate out so that there are 2 equations in 2 unknowns that involve A and C, and 2 equations with 2 unknowns that involve B and D. So we could solve these 2 separate systems many different ways. We could graph, we could use substitution, we could use elimination, we could guess. A lot of possibilities in terms of being able to solve these 2 systems to find out what the A, B, C, and D values should be. We're going to use the generalization of elimination in terms of matrices. So what we do is we start with our matrix 1, 2, 3, 4, and we augment it by putting the identity matrix to the right-hand side. And the process of elimination ends up converting the matrix that's on the left into the identity, and then whatever's left on the right-hand side is the inverse. So we want to go through the matrix, change this entry into a 0. The 3 needs to become a 0. Change the 4 into a 1, and the 2 then we want to change that into a 0. And doing so will change what's on the right-hand side, because whatever we do to a portion of a row, we have to do to the entire row, because this corresponds to equations. And so if you do something to one side, you have to do the same thing to the other side. So our first part is we want to make sure we have a 1 in the upper left-hand corner, and in this case we do. So the next step is to get rid of that 3. So to get rid of that 3, we're going to mimic the elimination process and multiply -3 times row 1 plus row 2. And when we do that, row 2 is modified. -3 times row 1 plus row 2 creates the 0 value that we wanted in this entry. And it also has an effect on the rest of the row. Well, at least on 2 entries in the row. Since that change was in the first column, it only affects the first column of the identity matrix. So then we want to eliminate or replace the -2 with a 1, and the way to do that is to divide row 2 by -2 and replace that entire row then by multiplying by -1/2. All right, so at this point, we have the 1 and the 0 in the first column, and we have the 1 in the appropriate entry in the second column. And now we need to eliminate that 2 that's here. And so we're going to replace row 1 with -2 times row 2 plus row 1. The idea of all of this is we don't want to mess up anything that we've already done. So this information to the left is going to stay fixed. We'll change the 2 into a 0, and then whatever other changes corresponding in the rest of row 1. And so we end up at this point, to the left of this line, we have the identity matrix. And so what's on the right is the inverse of the matrix that we started with. So to check this answer, we have our matrix that we started with. The matrix that we said is the inverse, and so we need to check to see if that gives the appropriate values. So we go through each entry. Dot product, so -2 plus 3. -2 plus 3 is 1. That's what we wanted it to be. And if we go ahead and check all of the other entries, we see that this does in fact give us the corresponding value, the identity matrix on the right-hand side. So this doesn't look anything at all like the matrix that we possibly would have guessed to undo the steps that are taken by the matrix 1, 2, 3, 4. But this is the matrix that does, in fact, do that. So the question that we might want to think about is what is happening geometrically? What does this matrix that we just calculated as the inverse actually do along the way? So we might apply that to the square, apply it first to the square and see what happened to the square, and then apply the other matrix to the square and see what's happening to the square. What do these matrices actually do? And then apply one followed by the other and see that the square does come back to the original position. So this process is a bit complicated in this way in terms of trying to go through and solve these systems of equations every time. So what we would like to be able to do would be to have a general formula. And so we start with a matrix ABCD with the identity on the right. And if we go through all the steps, we can, in many cases at least, will be able to create something with the identity on the left, and then the matrix on the right is the inverse. Again, this red line is just the separation between the original matrix and what we've done to it and the matrix that we are building from the identity. So what happens in the first case, we're seeing here that we want to put a 1. We want to have a 1 in this entry. So we say, okay, let's divide that whole first row by A. Well, we can do that so long as A is not 0, but if A is 0, then we can't do that division. In this particular derivation, we haven't worried too much about whether that value was originally 0. If it was, one thing we can do is switch rows. If you switch rows, it doesn't change the corresponding system. But it turns out that if that value was 0 and we don't really worry about it, the formula at the end, the matrix that we've derived, still actually does give the same answer, so long as, notice down here, there's this denominator in all of these entries, AD minus BC. And that denominator, as long as it's not 0, then it doesn't matter that A itself was 0. So take some time, go through these steps, think about what's happening, try it with some actual numbers, and see what we end up with. So the idea, again, is given the matrix A, B, C, D, then the inverse, by simplifying a little bit, we've taken this value, factored it out of all of the entries, and the A and D values have swapped places. The B and C values are in the same place, but the sign is now negative. And so for a 2 by 2 formula, for a 2 by 2 matrix, the formula says, let's start with whatever we have. If the inverse exists, this is what it looks like. This value AD minus BC is important if you don't have if this value is not 0, if AD minus BC is not 0, then we do have an inverse. If this value AD minus BC is 0, then our matrix does not have an inverse. So when the value is not 0, we say that the matrix is invertible, or we say it's non-singular. It's not by itself. It has a partner, right? Something you can multiply by it and end up back at the identity. The value itself, AD minus BC, looks like that value that we calculated in the cross product, and it's called the determinant of the matrix. If the determinant is 0, then we say the matrix is singular. There's nothing that we can multiply by it in order to get to the identity. The situation that would happen is if we tried to solve the augmented matrix approach, then on the left-hand side of our line, we would not be able to create the identity. And that's another way to tell that a matrix is singular. So what happens? A 2 by 2 matrix has a fairly concise way to describe the inverse and an easy check to see if the inverse exists or not. So if AD minus BC is 0, that inverse does not exist. We will care about larger matrices sometimes, especially with graphics related things. We don't get very big usually, 2 by 2, 3 by 3, 4 by 4. Occasionally we have some matrices that aren't square in different situations. But as far as the inverse of a matrix goes, we're talking about square matrices. And the steps we carried out in that process of putting the matrix on the left, augmenting the identity on the right, doing those calculations, that works for larger matrices as well. The problem becomes if the matrix gets very big, then the number of calculations and the number of steps in terms of carrying that out becomes pretty cumbersome. But the process does work. For the 3 by 3 or 4 by 4 matrices that are invertible, you can do that in general like we did with the 2 by 2, and you can write down fairly concise formulas that describe what happens in those cases. One of the ways to describe the inverse of a 3 by 3 matrix involves the cross product and the triple product. Remember, the triple product involves the dot product of a vector and the cross product of two other vectors. So the vectors in question can be the columns of the matrix, and the calculations involve the cross product of pairs of those, and also the determinant is given by the triple product. So we will come back to that again at a bit later time, but that's strictly for 3x3 matrices in that case. So what happens? The transformation that is created by a matrix, we can, in many cases, undo those transformations. Some transformations we do end up causing a problem with the determinant being 0, and so you do the transformation, but then there's no way to reconstruct or go back to where you were originally. As usual, if you have any questions, ask on Discord, email, in the comment section. Let me know if everything's clear or if it's not clear, and we will be able to try to clarify those concerns.